He has a long history of being part of IDEA. He was,
Second batch.
He's been at TA multiple times. Much more importantly, he's here representing himself as a deep learning researcher. And here that I, or TA, right? Really? He's going to be talking about that.
Yeah. Yeah, full disclosure, I will not be talking about my research. I will be teaching you what transformers and graph neural networks are in 1 hour and 15 minutes. So we're going to try to make it work. The good thing is transformers are extremely, in a way, completely different from what you've seen, but also in a way built entirely on things that you've already seen. And therefore, it's going to be very fast for you to understand if you've been paying attention last week. Graph neural networks are a little bit more different, but we're just going to do a quick introduction. So it's all going to be fine. All right, topic of the week. Let's start with transformers. So you've seen the easy version of sequence-to-sequence models like this, where you have an input sentence here in English, an output sentence here in German. What you do is you have the encoder, which is a recurrent neural network, encode iteratively each word of the sentence until the very last hidden state over there, which supposedly has the entire information of the sentence. And then you pass that as the input state to the decoder, which uses it to produce the correct output, so German translation or something else. You've also seen that in practice, this rarely, like regular tasks are rarely working with a model that's that simple. In particular, because you have a lot of memory issues where one vector state, like encoding an entire sentence in one vector state, is extremely challenging, and so you're going to end up having a lot of forgetfulness and not being able to produce the right outputs most of the time. And therefore, you have seen attention, where instead of using the last state of the encoder to feed to the decoder looks at all of the encoded states and decides, using something called an attention module, which one it wants to look at in priority. So each word is going to compute attention scores over each word in step in the decoder. You're going to compute attention scores over all the encoded states, figure out which ones are the most important, and use these weights to do a weighted average of the encoded states, and use that as the context that you feed to the decoder. Now, this works very well. Here's the question, though. Now that we're doing that, do we really need the recurrence at all? Because the original motivation for the recurrence was to have your final state actually represent the entire sentence. Now, you don't really need to do that since you have the attention module that does it. So what's the point of this recurrence? Let's say we remove it. Now you have a regular MLP that gets an output for each of the input words, and you try to attend on that. Question, do you think that's going to work?
Question, doesn't H3 depend, like in a vanilla RNN, doesn't H3 depend on H2 as an input?
In an RNN, H3 depends on H2 as an input, but does it have to? Like here, I just want to produce German, and I can look at all of the different words at the same time using attention. So what's the point of the recurrence? It's an open question. You're allowed to answer. We're going to make this interactive since there's a lot of people. Yeah. Correct. So this is, nice idea, but it's not going to be that simple, obviously, because, like you said, first of all, you don't have the order, and more generally, you don't have any sort of dependency between the words. you need to know which word in the sentence is the object and which word is the subject if you want to translate in German, because in German you have cases and declinations and stuff like that. You need to know which word comes first. You need to know all of these things. And generally speaking, you need each word to have a representation that takes into factors in the other words. And by factor in, I mean take into account the contextual information that the other words contain with respect to this specific word. It just so happens that you've already seen something that's very good at extracting context and generate meaningful representations from it, and that is called attention. So far you've been using attention on the to extract a context from the encoded states and use that for the decoded states. You may as well have the encoded states attend to each other and generate contextual representations like that. So if you do that, it's called self-attention. Yeah, like I said, what you're doing is for each word, you're gonna first extract some low-level features with like an MLP, a CNN, or whatever you want. And once you have these low-level representations that just encode the word itself, you're gonna use attention to extract information that represents this word with respect to the other words. So we're gonna dive into a bit more detail, although this should be very familiar to you because it's not that different from attention in an RNN. So once you have your H0 to H4, yeah.
I just wanted to understand what is the importance of positional encoding.
Oh, you're way ahead of us. We're gonna go to positional encoding later. So far, we're just
mentioned, right? What is the requirement for it? So you need to know the positional information as well for
so for now, what we're looking at is what word depends, to what extent words depend on each other. We are not in the version I'm presenting at this moment, which is simplified, using whether word is the first word or the second word, but keep that in mind because we're gonna go back there. So I'm not gonna answer this question at the moment. So you have your H0, H4, which you've extracted with an MLP. From them, you're gonna compute keys, queries, and values for each of the words using 3 different matrices with like an activation, just the linear layers that you already know very well. And then for each of the word, you're gonna compute its contextual representation. So that means that you're gonna take its query and you're gonna try to match it to the keys of all the words. And with that, you're gonna get a score. So we're gonna call the score of J with respect to I, E, I, J, and it's equal to the query of I, dot product, the query of J. Once you have these for each of the words, you can get a softmax over with respect to the keys, and then you get a probability distribution over the keys, which you can use as weights. We're going to call them W, Ij. And you use these weights to aggregate different values into something that we're going to call O, like output, which really is the contextual representation of word I. So O0 is represented over the figure. Yeah, like I said, it's equal to W sum of W0J times Vj for all of the J's, or just to attention of the query of, where W0J is the attention score of Q0 with respect to J. What do I hear? Are those questions on Zoom? Was that a question? Yeah.
So key and value have like one-to-one correspondence the way they use. So why do we have GNNs? Why do we need key prediction matrix? Why not just have a key matrix and a key matrix?
You mean key and what are you asking? Why are there 3 instead of 2? So in the most general framework, the key encodes the things you're going to be looking for in order to find which words are relevant, and the value encodes the things you're going to want to keep in mind when you aggregate. So the keys are just used to find the right words and compute the attention scores. The values are what's going to end up being used as a representation. Like intuitively, it's not necessarily exactly the same thing that you want in both cases. So that's why in the general framework, you have 3 matrices. You may want to do it with 2. You may want to do it with 1. You may want to use the encoded states directly. There's like a ton of versions of doing that. This one tends to work. Is the one that's in the original transformer paper, so I'm presenting that one. Oh, well, it's the same question I just answered, so hopefully they have the answer. There was a KQV in the version of attention that you've seen last week, wasn't there? I think, yeah. Yeah, it's the general version. Sometimes you don't use it, and that's fine too. In any case, this is how you compute output forward 0. And now this entire thing, computing the queries, the keys, the values, doing the attention, getting your weighted average and outputting that's going to be called like self-attention module. And this is like one layer. Nowadays, you can find them directly in most deep learning frameworks. So you're going to have 0, 0, 1, 2, 3, 4, all with the same formula. So this is self-attention in a nutshell. This is the only thing that you need to understand for today, for the most part. So is that clear so far? Yeah.
Could you go over again what the query encodes? You said the query is what we're looking for, and we're matching
up. The key is what you're gonna be. Like the query is a question that you ask, which is what should the the query encodes information of a word saying what am I looking for this specific word. The query encodes the answer to the question, like you should be looking at this. So you match the query of a word with the key of another, and that gets you the relevance of the second one with respect to the first. And that relevance, you use it just to get a score, and the score you use it to weight the value, which encodes what you're going to want to keep for the next layer.
Okay, so it's like an ideal answer to what we're looking for.
Sort of. Keep in mind that I'm doing like high-level explanations with English words of stuff that's just mathematical computation that seems to work. Can be a little it's a bit of alchemy to try to understand why some things work and some don't. But this is the high-level idea.
So just to make sure, the query is used to understand what attention do I pay to a particular word.
Mm-hmm.
Key is to fetch the value of attention of that word, and value is.
Mm-hmm. Yeah.
I mean, values used to compute the attention itself.
Like, imagine if the key and like, I'll give you, this is another version of explaining it. If the key and the query are the same, then the attention score of I with respect to J is going to be the same thing as the attention score of J with respect to I. And that means that, but it's not necessarily that simple, because if you have like an article like A and then a noun after it, it's not exactly the same thing you want to keep for the article and for the word. Like the article, for the article, you need the word in order to know what gender it is, if you're going to translate in German or things like that. For the word, you don't necessarily need exactly the same thing. So you don't want the key and the query to be completely symmetrical. Yeah. The softmax is used to compute weights, and weights need to sum to 1 so that you can use them to do an average. And with the weights, you're going to multiply them with the values and get a weighted average of the values. So yeah, you need to have the softmax before adding up the values. Yeah.
Do you ever apply an application while computing the query?
Yes, pretty sure you do. Let's go back to be sure. This is going slowly. No, I guess not. Not in this version. I've seen both in practice. You may want to have an activation or you may not. I think for the transformer paper, you do not, I guess. You don't need to know everything by heart except for the quiz. So yeah, anything else?
This, I think you mentioned that I get right. Repeat that part that you mentioned, right? But query also includes some information about the word, and key also includes some information.
Yeah, but in one case, it's the word that you're going to compute the representation of, and in the other case, that's the word that's going to be used in the representation. So it's not a symmetrical need of information. And like I said, if you have the key and the query be the same, then attention of word 1 with respect to 2 is going to be the same thing as attention of word 2 with respect to 1. And since words 1 and 2 play different roles in the sentence, you usually do not want to have that. Word 2 may need to look more at like if 2 is the subject, you're going to need to look at the object and at the verb. And if 1 is an article, you just need to look at 2. So query and key usually are not the same for that reason. What time is it now? Oh, not that late. Yeah, perfect. So you know everything about self-attention, which was the big one. More accurately, you know what a single head self-attention block is. You call it single head because in practice, in a transformer, typically, you will repeat that operation I just described multiple times in parallel. So one, not as like one being like the next layer, but more like as something happening in the width dimension. Where you're gonna have multiple different attention heads that are gonna do the thing I just mentioned, and that output the contextual representation in the end. And therefore, you're gonna have multiple, let's say 16 different contextual representation that you're gonna concatenate together to get your final representation. The reason you are doing this is that you may think that it's exactly the same thing as just having one attention head that's bigger. In practice, it's not necessarily the case because it makes sense that if you want to look at the different types of information when you're looking at context, let's say semantics and syntax are two different, or different functions of the words, what kind of semantic field do they belong to? These are all going to be requiring different attention scores, and you're going to want to keep track of different attention score sets when you compute your contextual representation. And therefore, it seems that it's better to have multiple heads than one, although some papers have argued in the other way. So don't take it as absolute science either. Yeah.
Do the heads work on the entire data, or is it?
No, they look all at the entire sentence.
Is it similar to GNNs in the way that
Yeah, pretty much. Pretty much. You can see it exactly like that, except like one filter just outputs one scalar value for each patch, Here you're gonna have multiples since the value itself for each of the heads is like a certain dimension, and you're gonna concatenate all of them.
How do you make sure they're not learning the same thing? Is it just random, like different random initializations? And then...
Well, they have different initializations, but like if they had the same initialization, would they end up learning the same thing? Presumably, yeah. Yeah, essentially you trust that if you don't do something, if you're not like in the what do you call that, like a deprecated mode of your of learning, where you end up in a well minimum because you've put everything to 0, you kind of trust the learning algorithm in the end to learn the thing that's going to be most relevant. And yeah, you need to handle initialization correctly if you want that to happen. Yeah.
So I just wanted to clarify that for these values and queries, how do we mathematically compute the weight matrices?
The weight matrices are parameters. So you just initialize them, you use them to do your computations, and in the end you have a big loss and gradient descent, and they're just going to learn themselves like usual. Backpropagation. Oh, sure.
Yeah,
Is that better if I join Zoom?
Yeah. So that we can just.
All right. I'm gonna need to find. I don't know where the Zoom is. I'm not on Piazza usually.
Oh, okay. No.
Okay.
I think we just need to go to this one.
That's okay.
All right.
I'm tracking the Zoom.
All right. We just need to go to.
Streaming link.
Yeah, I think it's stream.
All right.
Sure. And I will give you a host, and then you should be able to share your screen.
Okay. Sounds good.
Oh, yeah, you can sign.
Ah.
Like a blank screen, so you can sign.
I mean, sure, but like, what's the
Oh no, because you had to sign on Zoom, so that.
Oh, like the wait. I'm usually signing on with like the CMU
Oh,
account,
sure,
right?
yeah. Right.
Okay. I go back here.
Yeah, I think it's best to.
Okay. I mean.
Oh yeah.
Okay. Huh,
Right. Yeah.
Okay. Cool.
Cool.
All right. I join. Should I not have computer audio maybe? Yeah. Continue without audio. Got it. I am now.
Okay. I think you should be working.
All good?
Right. You can just hide it.
All right. Anything else?
Maybe just. You don't have to join.
Can we hide that? I don't know.
Yeah, you can hide it above, and you should.
Is it hiding?
Again, I guess. Join, and then yeah, that's good. So you mute it.
Mm-hmm.
Hiding.
It is not hiding. Can you hide it like
Try a hide video panel or hide. Oh no, it's not normal hide floating panel.
hide floating? Okay, good. Is everything working now? All right. Multi-head self-attention, yes? Sure. This one before? Sure. Oh, 1, 2, 4. There's a lag, sorry.
So here we're using the query of first we're using the query of the first and the key to the rest of the word, right?
So if you're gonna compute the output of H0, then you're gonna use the query of the query 0 and the keys of everything. Is it? No, it seems fine to me, no? Like the queries are in the I and the indexed by I, and the keys are indexed by J, and the attention scores are over the keys. So that seems fine to me, I think. Yeah, well, you need to use Q. You need to match Q0 with key 1, key 2, key 3. So yeah, it's just saying where you're going to do the dot product. But in the end, the output of that is going back to 0. Yeah, there you go. Better like that? All right, now you know self-attention and even multi-head self-attention. And we're going to add one multi-layer perceptron, which is just one layer with an activation usually after that. And now you have a multi-head self-attention block, which is the layer equivalent of a transformer. So when they tell you we use a 1000 layer transformer, it's 1000 layer times this, represented like that for short. You can pile them together, like I said. And now you have successfully removed recurrence in the encoder with just one caveat, which we are now going back to, which is that you are still ignoring the relative position of the words, which means that at this moment, if you like switch two words in the sentence, the encoder is not able to tell the difference. And that is a big problem because in that case, you can't know which word comes first, which is the subject, which is the object, which follows which. And that is a big problem, which you fix using something called positional embeddings, which are an embedding that is not looking at the word, but just at the position of the word. And so you're going to have a you're going to sum or concatenate, usually sum the H0 that we've seen, which is the low-level embedding of the words, and the low-level embedding of the position. What do you expect from this kind of positional encodings? One thing you could think of is I'm just going to assign a I'm going to do like what you do when you have a vocabulary and take one hot vector, and then you learn some kind of embedding for it. You're allowed to do that. It works, but you can do something that's a little simpler where you have a little less to learn, and it is to just assign directly the values to the positional encoding in a way that makes sense. By making sense, I mean that first of all, you want each positional vector to be different from the other ones. You don't want any kind of period. And second, you want the you want the relationship between two different positional encodings to only depend on the distance between the two. So you want, if you have P1, you have P2, you have P3, you're gonna want the relationship P1, P2 to be the same as the relationship P2, P3, and you want that to encode the notion of coming right after another word, essentially. Mathematically, you can say that you want your PT plus some distance tau to be simply a multiplier of PT that multiplier by something that only depends on tau and not on t. And that's pretty much all you need. So here is one big formula that does exactly what I just said. Not the only one, but it exists, and it's usually the one that's that we use. So you yeah. Yeah, essentially. And yeah, if you sum them together, you have both. So the positional encoding is gonna, yeah.
So the positional encoding essentially learns like order in a language, like subject verb object. That's like what's learned by that positional encoding, like all these rules that exist.
Just quick correction. The positional encoding encodes it. It doesn't learn it because, as you can see here, we don't. There's no parameter in there. It's just a function of the position. But yes, yeah.
So if we go back to this, right?
Yeah.
So you're adding the positional encoding to the word and passing that as an input to the model.
Mm-hmm.
So let's say you have this word I, you have this I,
Mhm.
pass a positional encoding to it. It still is could be visioned as a different form of embedding of a different word, right? So maybe that I becomes say we. It
Mhm.
changes the word. So how does positional encoding help? The way I see it is like you have a word embedding, you add positional encoding. It disrupts the initial word embedding and maybe changes it.
It's not a question of like changing it like that. It's more that before you didn't have any information about order to use, and a network cannot just learn things that are not in the input. So if you give the words without any order, just as like an unordered set of words, the network can't learn what's the right order for the words. So, for example, I don't know, Jack is taller than John is the same sentence for a transformer as John is taller than Jack. That seems like a problem because then what does taller mean? It's not symmetrical. One's supposed to be the object, one's supposed to be the subject. So you want some form, like you want the position of the words to be in the data in some form. That's it. In the RNN, you didn't have that problem because the RNN naturally has position since it sees the first word first and then the second word second. Yeah. You could. I don't know if that would get good results. In practice, you tend to some. I think. Don't be surprised if you see a paper that says we concatenated other questions. All right. Yeah. So here's a complicated formula that you're gonna remember, but don't think too hard about it. You encode the positional encoding is going to be a bunch of sines and cosines that have different frequencies. So usually you have the sine and the cosine for one frequency, then you add another and another and another. This has some nice properties, like we've discussed. It's not going to repeat. If you take two different t's, you're not going to have these. You're not going to have these to be the same as long as you don't choose your w's, your omegas. I mean, to be the identical or multiples of each other or something like that. And you have this very nice relationship between PT and PT plus 1 or PT plus 2 or PT plus K, which is that the second one is the first one multiplied by a block diagonal matrix of this form, which is a property that you can easily derive using high school level trigonometry. So I'm not going to do the derivation of that. But that's it. And that usually works very well. If you're wondering if you prefer to learn encoder positional encodings instead with parameters, yes, you can. Transformer initial paper says that it's pretty much equivalent. Yeah.
How does the figure relate to?
it gives you the values of PT for different values of T. So you have, I don't know what the values of omega D and D and L were in that case, but you have the dimensions on the y-axis and T on the x-axis. And it's here to show you that they don't repeat because they have this that's basically what they look like. You see this this figure a lot, so it's okay. Yeah.
What is symbol tau signify?
Tau is like T plus K, but K is a time, so we're gonna call it tau because it's Greek and it looks like T.
It shows the relationship between one time and k times.
Yeah, it's like a time difference or time delay or yeah, just a notation. So you have your positional encoder. Yeah.
Just one thing. Is the T plus tau, are these positions absolute? Like if
they
you
are
start a
absolute.
sentence with 0, 1, 2, 3, is that
They are absolute, yes. But it's if you're thinking, okay, what happens if I see T 10,000 because I have a very long sentence and I didn't have that longer sentence in the training data? It's actually not that big a deal because you have this relationship, this linear relationship between one word and the following, which is the only thing that you're going to need if you want to compute good attention scores in the end. You're just going to multiply the matrices together. So only the value of the little tau is going to end up being relevant, which is exactly what you want. It's not like it's interesting to know which word comes first. It's more interesting to know which, compared to a word, which one comes next. Yeah.
You say it never repeats, you say that the positional
Yeah, I mean, if you take T1 and T2, PT1 is not the same as PT2, whatever the T's you pick. That's what I meant. Yeah. Decoding? Yeah. Oh, we're getting there. One thing at a time. But yeah, there are 2 slides ahead. So right now we've removed recurrence from the encoder. I think we have all the elements we need to do that, which are attention, multiple heads, and positional encoding. And you have a self-attending encoder. Now, can you do the same for the decoder? Yes. Yes. Right answer. Is it exactly the same? Yeah. Exactly. Good job. So you, in the encoder, each word depends on, like, you build the context of each word using all of the other words because you have access to all of the other words. In the decoder, the goal in the end, in training, you have all the words, but in testing, you do not. And at inference time, what you want to do is decode the words, and you're going to do just like with the RNNs, you're going to decode them one by one, starting with the first. Because of that, since at inference time you cannot attend on the next words, at training time you cannot do it either. Otherwise, you're going to learn things that you eventually do not use and do not match with probability distribution in the real world, and that's a big problem. Therefore, you're going to do exactly what we've done so far with just one tiny change, which is that you're going to use masked self-attention, which means that you're going to compute your attention scores, and once with all the words, and once you have them, you're going to force all of the attention scores for the words next to, for the words that are occurring later than T to be 0 by multiplying your weights with some triangular matrix of ones everywhere, and by renormalizing in order that the weights keep summing to 1. And that is a masked self-attention block. And apart from this one little change, it's exactly identical to the self-attention that you already know. So you're gonna have multiple layers and an MLP in the end, just like in the encoder. And we're gonna call that the mask multi-head self-attention block. And now that we have that, we have our encoder that doesn't have any recurrence and just uses self-attention. We have a decoder that doesn't have any recurrence and just uses self-attention. And in the end, in the middle, we have the attention that you already know that the decoder uses to get information about the encoded states. It's computed over the encoded states of the final layer, the final attention block of the encoder. And since now we have attention everywhere, the word can be confusing. So we're going to call that cross attention as opposed to self attention. And that's it. So that's a transformer. It's just that plus a bunch of layers, a few optimization tricks that you can find in the paper, but that's most of it. The rest of the transformer lecture, we're gonna go fast because we still, well, actually we're not that way, but still, yeah.
Is there recurrence?
Is not. But you do decode the words one by one when you're at inference, but that's not, you don't have recurrence in the same that you don't have a recurrent neural network. Yes? What's the question, sorry? To fixed length input, no. It's the transformer is a sequential model. So you can put as many words as you want. And that's what the attention is for, right? If you had fixed length input, you can just use a linear layer to do everything and it would be great. But you want to be able to encode word level that takes into account an entire sequence whose length can change. So everything I've said, you can use with length 1, length 2, or length 1000. And with that, you can make batches of variable length, just like an RNN, and you just need to, not attend on the part that's padded in the batch, just the usual stuff. Yeah. This one.
And I'm misunderstanding that it looks like you're still recurring.
I'm gonna go ahead and say that this is an error in the figure. Yeah, I didn't pay attention to that. These arrows needs to be removed. The information about the previous words is used, but only in the form of self-attention. And also, like if you're decoding, you use the word, the output of a word as the input of the next. Yes.
I think I'm blank for a second when you said self-attention, like cross attention is different from self-attention.
So before you call attention the thing that attends on the encoded state to get decoder information. That's how you saw it last week. Now we have attention that just is used separately by the encoder for itself and by the decoder for itself, and that is called self-attention. But we're not going to call one self-attention and the other one just attention. So to make the difference, we're going to call the attention that you've seen last week, and that is in the middle in green, we're going to call it cross-attention from now on. And attention is a ensemble term that can mean either of them. Yes?
In fact, the decoder needs a representation of the first go over all the math, the attention blocks to get the output of the first word and then feed that to the next.
But you only, in order to get the first one and feed it to the next, you on that's something you only need at inference time, right? At training time, you don't need that. You compute attention over the entire sentence. You just make sure that you mask over like the next words, and therefore training is fast. Inference is still long but it's not longer than it was with the RNN if you account for the fact that you have a lot of layers here. Mm-hmm. A question?
So you're saying that you generate the output of the first step, like you get to say ish,
and then you pass it on to the next step. Doesn't it all happen in one go? Isn't it supposed to be parallel?
I'm talking like this represents to you the decoding. You call that I think you call that teacher forcing sometimes in algorithms. So you can use that in the training as well. It's like each the decoder in the real world is not going to have access to any words in the input, right? So you're gonna use the start of sentence first, compute the first word, then use that as your input for the next word, and compute the word iteratively until you get to end of sentence. That's something that I think is identical to what you've seen for the for RNNs. But you only have this sequential nature of computation at the inference time and not at training time.
The training time remains, you can parallelize it, but inference is sequential.
Yes, we're gonna go to parallelization like a tiny bit later, but yes.
So inference time, you compute the attention weight at every time.
Yes, but you don't need to compute all of them. You just have one new query. You're gonna you can compute the keys of a word, and then it doesn't change anymore. And then when you get a new word, you compute the new query. You match it with that key.
So you normalize every.
Yeah, you know whatever you can not recompute, you are not gonna recompute. But yeah, that's just optimization. If you use PyTorch NN.transformer, which I think exists now, I think it's going to do all of this for you. But yes, if you're going to have to implement a transformer one day, yes, you pay attention to these things. Yeah.
Next slide. So how do we do the positional encoding here?
The positional encoding is just a function of the input positions. So you have 20 words in your input sentence. You have a positional encoding layer that's already implemented in Hugging Face, and that's going to do the formula that we've seen in the slide with the cosines.
So like we have a vector of this positional encoding. So how do we combine the
you sum them up. You have an input embedding that you compute with MLP, a positional encoding that you compute with its own layer that doesn't have parameters again, and then you sum them up and you get your input to the transformer. Yes.
So during the training, when you're going to the decoder, you always use feature forcing.
Depends. You can use some amount of teacher forcing or not.
You have to have that sequential dependency there. If you don't use feature forcing, wouldn't that slow the training?
It does slow the training, yes. So sometimes you use it, sometimes you don't, sometimes you use it just at the end. At this point, it's just optimization. I'm gonna leave all of this to the recitation that you're gonna have on the topic because that's more hands-on things. Yes.
We are already doing the positional encoding for the input, and when we are getting the output, we are doing the positional encoding.
Well, you know that you need it in training because in training it's the same case as the encoder. In decoding, if you were always decoding, you wouldn't need it. But now, if you train the model on it, then it needs to have it every time, right? So you're going to use positional encoding at all at inference as well because the model is trained on this positional encoding. All right. 25 minutes. So yeah, I'm gonna rush to the end of the transformer parts and answer some questions at the end of the transformer parts, depending on the time we have left, and then move on to the GNN part. So the transformer is a very good sequence-to-sequence model, as represented in this table that was in the original "Attention is all you need" paper. Essentially, if you use a model that's as big as like the previous models, it can compute a lot faster and keep roughly the same performance. And you can pile more layers and make it a lot bigger, and then you get even better performance. Why is it so? And it's when I say it's faster by like 1 or 2 orders of magnitude, depending on the model. Why is it so powerful and why does it compute so fast? One of the reasons is that it essentially fixes the problem of a vanishing gradient of the RNN that you have seen. An RNN, once you unroll it, is just one very, very deep network where the gradients of the last word are going to have to backpropagate up until the very first word. And then that's in the decoder, and then they backpropagate through the encoder as well. And the number of layers is proportional to the number of sequences, and because of that, you have a bunch of vanishing gradient problems, exploding gradient problems sometimes, vanishing memory, etc., etc. And with the transformer, you do not, because the depth is only dependent on the number of layers that you pack, and that makes learning a lot easier and enables you to scale transformers much easier than you could scale LSTMs. Recently, there's a paper that does 1,000 layers of transformer. I don't think you've ever seen 1,000 layers of LSTMs. The second reason is that because in training, you do not depend on the processing order, contrary to the RNN where you need to compute YT in order to get YT plus 1, then you can parallelize computation in a much more efficient way and leverage a machine with like 1,000 GPUs on it and train models that are extremely large. And that is one of the key reasons why transformers have enabled an incredible gap in both model size and model performance in the past 3 years. Yeah, so in transformer, like I said, you only have a bunch of dot products to compute. If you make this all together, it's just one very, very big batch metric multiplication problem, which is extremely easy to parallelize. So transformer is a very good sequence-to-sequence model. Sequence-to-sequence is one of the ways you can use RNNs, as you have seen either last week or the week before. But once this model was on the table, people have realized that maybe you can apply the same idea to every context that has RNNs. For example, you've seen language models. A language model, a generative language model, is something that it's like historically an RNN that takes inputs and like a sentence and learns from one word to predict the next word. You can do that with a transformer very easily by just taking the decoder part of the transformer. That's called a decoder-only transformer if you want. And the canonical paper that does this is called GPT. Yes?
So in this diagram, we get two inputs from the input encoding data. So the left one, from that we get two inputs to the multi-head attention, and the outputs give one input to the multi-head attention.
Yeah, I'm just putting the original transformer over there. But really in GPT, you ditch the whole left part and you just keep the right part.
But we generally get three outputs, right? Keys, values, and query.
Yes.
Two inputs to that one and one input from.
No, the keys, values, and queries are all computed from self-attention in the decoder, and so they're all computed from the decoded state, the decoder state. So they're just like you've seen at the beginning. Within the encoder, you replaced the recurrence by computing keys, queries, and values. In the decoder, you also replace the recurrence by doing keys, queries, and values, just using the inputs of the decoder. So this really works as a language model. You give it English sentence, it outputs English sentence. Again, yeah, I think we're gonna have to go fast and skip the questions, but feel free to come ask more in the end. So yeah, that is GPT. I don't know if you've heard of it, but maybe you've heard of GPT-3, which is exactly the same thing, but bigger. And you add something cool called task conditioning, where essentially you take your input and you put the task that you're trying to do in it. So you'd have like an English sentence and then translate to French and then a French sentence. You feed that as your input. And then if the model learns to generalize on that, then it also learns incidentally to translate from English to French. And a fun thing is that in that case, if you generalize, you don't just generalize to more data, but you also generalize to more tasks, since the task is now part of the input data. And you can do things that you may have heard of, like prompting and zero-shot learning and all of this cool stuff. And this works because transformers are so good at scaling and at computing in parallel. So yeah, that is GPT. The other big one that you may have heard of is BERT. BERT is just the encoder part of the transformer. It is trained using you put blanks in the input sentence, and then you learn to reproduce the same sentence, but by filling the blanks. And so what it learns is to compute very good representations. Contrary to GPT, which tends to be more of a zero-shot model that you just immediately use, BERT is just it's like a pre-training for embeddings, and then you tend to use these embeddings as input for all of your models and by doing fine-tuning. This is very related to representation learning that you will learn more about on Thursday, I think. So to recap, with self-attention, you can effectively replace recurrence in sequence-to-sequence models. That's called the transformer, and the major caveat to remember is that you need to add positional encoding, otherwise you don't have any form of positional information. And it can be used in order by keeping just the encoder or just the decoder, just one or the other, depending on context, in order to replace most of the sequence tasks that you have seen, and even sometimes non-sequence tasks. You can use computers for computer vision. In that case, what you do is you take your image and then you kind of treat it like a sequence. You divide it in patches, and each patch gets its own positional encoding, and then you feed that to a transformer and you get your output. You can do classification, you can do everything you want. And that is interesting because it shows that transformers are, in a way, have flattened the field of all the tasks of deep learning and kind of made them all the same. A sequence and an image are pretty much the same thing. Speech, video, all of these are just variations of the same thing, where you have a big bag of individual elements that have a relationship to each other. And therefore, one of the big practical impacts of transformers in the past few years is that now if you just go to the one website where all people put their models, and because of all these models are built using the same basic blocks of transformers, that's very easy to do. And you can just pick your model, pre-train it or fine-tune it, or do one of these things. And apply it to the task that you want to do. And it is in the practical applications of deep learning in the real world or in companies that has played a major role. Don't, however, think that deep learning is solved and you don't have anything to do, because it's not that simple. First of all, I'm just going to give you two caveats among many. There's an incredible literature on whether transformers are good or not good, or what did they do good, and are they really that better than any? Just read them if you're interested. I'm just going to give you two small elements. First of all, not all transformers are the same. The way you train it, what you train it on, is extremely important. Some of them are very big, and some of them are specialized in being fast, and some of them are just trained on English, and others on multilingual data. There's a bunch of objectives that you can pick from, and be sure if you're going to use a transformer, let's say for your deep learning project, that you're going to pick the right one. Second, it's not always the transformer that's the best suited architecture for your problem, contrary to popular belief. One of their limits is that at equal performance, you're going to tend to need more parameters in a transformer than in some other architectures. And that means that for everything that's Internet of Things related, applications that run on your phone or on your Alexa device at home, transformers are still a little lagging behind in that, and you still see a lot of LSTMs and even things that are older than that. And yeah, that's it. Questions? We have 15 minutes. Okay.
I have a question for the positional encoding part.
Mm-hmm.
So, so you just mentioned positional encoding gives the position information about a particular word.
Mm-hmm.
Now, for example, say I have two sentences, and in my first row, I take the first sentence, and say I have some part of the second sentence, and then I get position encoding. So for the first sentence, I can get my output properly, but the initial part of the second sentence, which has also come as an input into the transformer. So how
You're
do
talking
you
about
do-
encoder inputs or decoder? Like the second sentence is the decoder input
Yeah,
in your
in
example?
the encoding part. Because
Oh, in the encoding part.
Yeah.
So you have two sentences and they come one after the other in the same input?
yeah, so you have start of sentence, end
Ah.
of sentence, and it say 3 words from the next sentence. In that case, how is the position encoding?
Typically you would like if you have a sequence, you treat it as one sequence. So the last part is like like the next sentence, I guess, is going to have the next positional encoding. If you have a point to make the distinction between the two sentences, and your transformer is supposed to handle like documents instead of just sentences, then it's going to learn to recognize that points mean the end of a sentence and that you start another one, probably. That's yeah. Sure. So a vision transformer is just like a transformer, except its inputs are representations of patches of an image. So you cut your image in 9 parts or 32 parts, I don't know. And each of these is going to be one fixed length, fixed size little input that you can pass through a linear layer. And then you get a H0, H1, Hn, etc. And each of these, for each of these, you're going to have a positional encoding as well. It's going to need to like handle 2 dimensions, your positional encoding, which might be a little different. If you want to know how to do that exactly, to be fair, I don't know, so I can't give the answer, but it doesn't seem that complicated. You just have 2 dimensions instead of 1, so you give the position in 2 vertical, horizontal, and concatenate them. And after that, everything is exactly the same as a sentence. You pass that through a transformer encoder, and then you have you can aggregate, get to a final linear projection, have your class, and compute cross entropy loss, and yeah.
So you said for translation model, you said for a translation model, transformers reduce computation for the model. When caveat 2, you said they also require more parameters. I don't understand.
They reduce computation time if you have a lot of resources because you then compute things in parallel. But there is not fewer matrix multiplications or parameters than there was before. That's the difference. Okay, I'm going to try to go through. Okay, GNNs. I'm just going to do a quick introduction, so that should not be too long. And if we have time after that, I'm going to answer more questions. But since it's 10 minutes, I don't think we will. So you've seen models for a bunch of different types of inputs, like fixed size, like shift invariant images, like sequences, and even transformers that can do a little bit of everything. There is one big class of data structures that we have not talked about, and that is graphs. If you have done a CS data structure class in the past, you already know what a graph is, but I'm still gonna explain in a nutshell what that is. It's a structure that is used to have a representation of entities that have a relationship with each other. So it's gonna have two major sets of elements, which are the nodes or the vertices, which are entities, and the relationships between them, which are edges. Eventually, it can, I mean, if you have a graph is usually the combination of these two things. You usually also have attributes for the nodes or even for the edges. You could have a color for each or some kind of topic or label for each of the nodes. You could have a weight for each of the edges or even a direction. A bunch of data is very efficiently represented as a graph, like a social network where the people are nodes and who is friends with who is the relationships. Like a website, like the entire World Wide Web where pages are nodes and hyperlinks are relationships. Papers on archive that cite each other, molecules that are like atoms and then bonds between them, etc., etc. Generally speaking, even whatever problem you pick, you may find some good way to represent it as a graph. Just one example: if you have an image, you can say that a pixel is a node, and then pixels that are next to each other have an edge between them, and that gives you one very big, very organized graph, such as this. Now, why is this relevant to us? Okay, sorry. So like I said, edges can have a direction or not. For us, they will, but you know, it's like you can say that any graph is a directed graph by saying that you have one edge in one direction and one in the other. Why is that relevant to us? Because you can compute some tasks on graphs, such as, let's say, node classification. So in the case of papers that are linked by citation, you may want to, like each paper is going to have a theme, like NLP, computer vision, speech, biology, etc. One thing you may want to do is be able to automatically classify a paper into a theme, and that can be useful if you want to have a data, like if you're managing a database of papers. You may want to do link prediction, which is means trying to predict, given two nodes, if there is going to be an edge between them. You can try to predict something about the entire graph, like image classification and the image graph, that case that we've seen. And there is a ton of very classic combinatorial problems with graphs that you may have heard of before. And many of them can actually be formulated as some kind of machine learning problem as well if you try hard enough to modelize them. To do that, we use something called a graph neural network. We're gonna run through just one simple example where we're trying to do node classification. So like NLP or computer vision type of the task. The way to do that is you're going to start by having your graph, your vertices and your edges. And each graph is going to have some kind of initial feature representation. I said that graphs could have attributes. That's the attributes. In the case of papers, the attribute can be some kind of representation of the document, TF-IDF, any kind of NLP thing that you can use to represent a 8-page PDF. And the edges are citations between papers. This is your low-level embedding, and this is what you're going to use as inputs. What you want to do is have an embedding that is not looking just at a paper, but also taking into account all of the papers that are related to it through citations. So that means computing contextual embeddings pretty much for all of the nodes. So to do that, we're not going to use a transformer this time, although you can use a transformer for these kind of things. We're just going to use a multi-layer network. It's fairly similar to an MLP, but with like one little trick in the middle. So it's going to be a multi-layer network, and you're going to have one for the KF layer is going to be the different like the KF intermediate representation of each node. We could do a representation of the edges to do some tasks. Here, that's not relevant, so we're not going to do it. To do that, to pass from to compute the k plus 1 layer from the KF layer, you need actually 2 steps, which are to aggregate and updates. Aggregate means gathering all the information from the loads that are linked to your node. So let's say the node is going to be called, how do we call it? We're going to call it U. So node U is going to be linked to node V, node W, node Z, etc. You want to aggregate the information of all of these nodes into something that we call a message for U. And then you're going to use this message to update the representation. Concretely, aggregate means that you're going to, for example, sum all of the HK of B, HK of W, HK of all of the nodes, and into the message. And then update is going to be one linear layer that takes as input both HKU and the message KU, MKU. So yeah, to formalize it a little bit, MKU is going to be the sum of HKV for all of the V neighbors of U, and yeah, sometimes the nodes may, like, this message can be 0. That's not particularly a problem. That just means that the node doesn't have any neighbors, or that like if they're a directed node, they may have like edges going out but not edges going in, and that's fine. That's also something you want to encode. And then you have your linear layer that is gonna have a weight matrix for HK, an output of HKU, an output of MKU, and some bias BK, plus some activation. Tan H and ReLU are both typical examples of activations in that case. And that's how you get HK plus 1 U. So you just repeat that for K different layer, and in the end, you're gonna have your final embedding. And to train that embedding, you're gonna train it to do the classification task that you want. So you pass it through one final linear projection that computes some kind of output over all of the themes that you have, and you compute your divergence, your cross entropy classification loss from this. And you train like that. The parameters are just the matrices that take into account the message and the representation. And yeah, apart from this tiny thing that you have to aggregate the messages from the encoded nodes, is just a multi-layer perceptron as you already know them. Now, what is this used for? In practice, I gave you an example, but like GNNs have practical use in very concrete applications, and you've already used them unknowingly. For example, one of the things that one of the breakthroughs that have been happening some time ago is DeepMind has managed to build a big GNN network for doing traffic prediction using Google Maps data as a graph. So you aggregate segments. The segments tells you how places are connected, and then you compute use all of the data about past traffic that you have to train the model, and you learn how to predict from a place and a time on the map how bad the traffic is and what's your estimated time of arrival. And there has been extremely significant improvements in the ETA prediction of Google Maps thanks to GNNs. And yeah, we're done. So yeah, that's it for me. We have 0 minutes for questions. So yeah, thank you for listening.